Hi everyone, I'm Miaoqian, a PhD student from Chinese Academy of Science. I'm glad to introduce our paper, Detecting API Post Handling Bugs Using Coin Description in Patches. This work was done with Chen and Yaoxian, who are also from CVEs. As we know, application programming interface, or API, are common in software development. As this API can cause various effects, developers should be cautious when using them. API post handling, short for APH, handle API's effect after API call. Improper API post handling can cause various security issues, like non-pointer dereference, memory corruption. In practice, it is common for developers to make mistakes on API post handling because they don't know how to perform the handling, leading to bugs. The rep style showed two patches for APH bugs, facing improper error check and missing resource release after API call. So how can we detect these bugs? The common way is referring to API document, which describe API usage specification. For instance, the document of kobject init add an API in the Linux kernel describe how to perform post handling for this API. If this function returns an error, kobject put must be called to properly clean out the memory associated with the object. To detect this bug, we can check whether the API usage in the source code adhere to this specification, and any violations are considered as bugs. So first, we need to have specifications. Previous work has proposed to extract specification from API documents. However, this document can sometimes miss critical information and making bug detection infeasible. Consider the patch shown on the right. It addresses a memory leak in the Linux kernel caused by improper post handling for USB create HCD API. The previous code didn't release the memory allocated by the API call. To detect this bug, we need to know the post handling way for the API. However, the API document don't provide this guidance. Another approach is to infer specification from API usage in source code. However, the usage might not always be correct. Without reliable specification, detecting APH bugs becomes challenging. Given these problems, it's essential to explore alternative sources with APH specification. In our study, we find that bug patches are valuable sources for APH specifications. As illustrated on the right, these patches fix bugs indicate the correct way for API post handling. If we can extract APH specification from these patches, we can detect new APH bugs associated with the same API. However, the patch code contains other details beyond API usage. Thus, we need to know what to extract and identify the essential information from patch code. Therefore, we first formally define APH specification. This will guide us in determining what to extract from patch code. Specifically, with API document, we identify the 4 key elements that make up a specification. They are target API, post operation, critical variable, and path condition. The target API is the function requiring post handling. In this case, it is kobject init add. Next, we have the post operation, which is performed after the target API to handle its effect. Here is the kobject put. And the critical variable is the variable affected by the target API and requires the post operation, which is the object. Moreover, there could be some conditions for applying post operation. We use path condition to categorize this. Now let's put them all together. Our defined specification implies that when the path calls the target API and the condition are satisfied, the post operation should be performed on the critical variable. With this, let's look at how a patch contains these elements. As we can see from this example, in the patch code is the target API call USB create HCD allocate memory for the critical variable for HCD, but it didn't release the allocated memory. To fix this bug, the patch added the post operation USB pull HCD, and the corresponding path comes with its own conditions. It's clear that these elements are all within the patch code. Based on this, we propose to extract specification from patch code. Specifically, focus on the 4 key elements. It's clear that target API is contained in the patch code. However, there are also many other functions. This brings us a question, which one is the target API? Ideally, if we understand the behavior of all these functions, identify the target API would be straightforward. However, understanding these functions could be quite challenging. In our study, we found that patch description often explains the rationale behind the patch. For APH bugs, the target API is the most critical element, and the developers usually highlight it when explaining the patch. In this case, the description mentioned that USB create HCD will allot memory for HCD. Therefore, the patch description can provide valuable information for the target API. Based on this insight, we present our tool APHP, which stands for APH bug detector using patches. APHP automatically obtains APH specification using code and description in patches, and then use the specification to detect new APH bugs in target programmers. The workflow is very straightforward. It consists of 2 phases, specification extraction and bug detection. Specifically, the first phase takes patches as input and extract specification from them. Each specification follows the format we defined before. The second phase further utilizes this specification for bug detection and report potential bugs. Next, we continue with the example to explain how APHP works. The first step is to extract specification. As shown in the middle, given a patch, APHP extracts the 4 elements one by one. Specifically, APHP first identifies the post operation. Because patches for APHP bugs usually contain minor code differences, which is closely related to the post operation. So it is the most easiest element for extraction at the beginning. In this case, APHP extracts the post operation USB pro HCD first. We skip the technical details here due to time limit, and you can refer to the paper. Next, APHP determines the target API. It first identifies all target API candidates through data flow analysis, then utilizes description to infer the most likely one. In this case, APHP first obtains candidates including USB create HCD, HCD to OSU, and USB add HCD, as they have data dependence with the post operation. Then APHP utilizes the description to infer that USB create HCD as the target API. After this, APHP identifies the critical variable, as the variable name can change in different contexts. For generalization, we use its relative position to the target API to represent it, like return value, the first argument, and so on. In this case, the critical variable is the HCD, which is also the return value. Then APHP collects the path condition along the corresponding path. This step follows the method from previous one, and we omit the details here. Finally, APHP obtains an APH specification and then uses it to detect new bugs. The bug detection main idea is to find the path that calls the target API and the condition and satisfy the conditions, then verify whether the post operation is correctly performed on the critical variable. If the operation is missing, APHP reports it as a potential bug. However, analyzing every path in program like the Linux kernel is expensive. To resolve this, we introduce the APH specification-based graph, or ASG. The ASG is a subgraph of the control flow graph, preserving only the APH specification relevant code. Based on this, APHP first finds the target API's caller. For each caller, APHP further generates its ASG and check each path with it. To illustrate, let's look at the example on the right. It is the ASG of a caller of USB create HCD. Here, APHP analyzes each path in the ASG and identifies the path that satisfies the conditions. It then finds one buggy path that failed to perform USB pull HCD on the critical variable and report it as a potential bug. By now, we illustrate how APHP works with a given patch and then detect new bugs. Next, we go to the evaluation. We evaluate the tool on 4 popular programmers. From the bug report generated by APHP, we manually confirm 410 new bugs. These bugs, on average, have existed for over 5 years and can cause various security impact. We also submit patches to fix these bugs, and about 200 patches has been accepted so far. We also compare APHP with 3 types of detectors, including patch-based detector, VADI, and MVP, document-based detector, advanced, and source code-based detector, IPPO. Results show that these tools fail to detect the majority of APH bugs identified by APHP. We also perform studies to evaluate each component of APHP. The first table illustrates the importance of patch description. Here, we compare APHP with APHP minors, which is without patch description. Our study revealed that description held to extra accurate specification, thereby improve precision in bug detection. The second table shows the contribution of ASG generation. We use metrics like the number of nodes, number of paths to analyze the scale of CFG and the corresponding ASG. Compared to original CFG, ASG generation significantly reduced the amount of code analyzed, enable APHP to scale in large programmer. We also investigate the new identified APH bugs and have several findings. Specifically, we found that certain error-prone APIs can cause hundreds of bugs. For instance, open firmware device tray APIs in the Linux kernel, which are shown on the right, provide access to hardware devices are often misused. Moreover, some APH bugs arise due to in-place usage specification driven from programming-specific conventions. And these specifications are not mentioned in the API document. Developers who are unfamiliar with the programmer are likely to make mistakes on this. Also, some API designs are quite counterintuitive, leading developers to make mistakes. Our findings offer valuable insight into the characteristics of APH bugs and aid the community in both fixing and preventing such bugs. To summarize, our study proposed a novel approach that detects APH bugs using code and description in patches. APHP detects numerous new bugs in popular programmers like Linux kernel and QEMU. Based on these bugs, we also provide valuable insight for community. APHP is also open source and available on GitHub. Thank you for your attention. And any question?